Good evening and welcome to EdSofta. Okay, my name is Radioactivity, and and I'm glad to welcome you to today's tutorial session. Okay, today we're going to be talking on radioactivity in physics. We've been doing this since two. We've talked on vectors, talked on electricity, we've talked on projectiles. So, and right now we're talking on radioactivity. Okay, so firstly, this is brought to you by EdSofta. It's a tech company that specializes in creating solutions to help students pass their exams. That's EdSofta for you. So we currently have two apps in the market right now, helping students prepare for their exams. EdSofta SSCE and EdSofta UTME. EdSofta UTME is an app that prepares students for JAMB UTME. It has past questions, study materials, and many other features that help students prepare for the exam. It solves the problem of having to familiarize yourself with a CPT exam, and has a very nice user interface and a couple of other features and solutions to help optimize the preparation for these exams. Okay, so for this tutorial, we would be solving questions from the EdSofta app. Yes, the EdSofta app has lots and lots of questions for us. And then for you to, if you want to have the app, which I would advise that you do, we have the app runs on Android and Windows, so you can install it on your mobile device, and I would preferably an Android device, and your PC, which is your Microsoft Windows system. Okay, so to install it on Android, you have to go to Google Play. You can go to Google Play and search for EdSofta UTME, and then you can find us there, or you go to the website www.edsofta.com, and then you click on products, and then you can see a list of products that we have out right now in the market. Okay, and then you can download for either Android or PC. Okay, so let's jump right into it. Okay, radioactivity. Okay, so I'm just going to have a brief discussion on what radioactivity is before I now talk about what is on the slide. Okay, so radioactivity has been around for a very long time, and we've used it in lots of fields. It has been used in what is it called? It has been used in medicine, agriculture, and the likes. But it all goes back to the year 1896, right? 1896, a guy called Henry Becquerel, discovered that uranium compound placed on a photographic plate, which was covered with life-proof paper, would cause fog to fall on the plate, Okay, so it was an experiment I was trying to do, and that's when he discovered some particles, some rays and some particles. Then a couple, Pierre and Marie Curie, in 1898, that's just 2 years after that, detected some radioactivity in the element thorium, and noted that the level of radiation in a natural occurring uranium ore, called the pitch blending in that time, was much higher than could be explained by its uranium content. And unlucky for them, maybe to understand this, they were exposed to so much radiation that they died as a result of that. Okay, so it shows you, in as much as it has its good sides, it definitely has its bad sides. Okay, so now when we talk of radioactivity, yeah, we're talking of different kinds of of rays, right? And the three most common ones are the alpha rays, beta rays, and the gamma rays. The alpha rays, the beta rays, and the gamma rays. Okay, so now this is just a table that just shows the difference, and it goes to explain each ray and the differences between them. So the alpha ray has a positively charged particle, beta ray is a negatively charged particle, and the gamma ray is an electromagnetic wave like light or X-ray. So there are different types of gamma rays. So note, alpha ray is positively charged, the beta ray is negatively charged, and the gamma ray is an electromagnetic wave, so it does not really have any charge. Okay, so it's an alpha ray is deflected by the electric and magnetic field, which is possible because it has a positively charged particle. So, and because it's positive, it would naturally tend towards the negative field, negative charges in the electric field. So there was an experiment that was conducted where he released a bunch of rays, and then they noticed something, that some rays tended towards the negative side and some rays tended towards the positive side in an electric field. And while some just went, they weren't really bothered by the negative or positive plates in the electric field. So that's how they came to find the distinction. So alpha rays tend towards the positive side, so the negative, because they already have a carry a positive charge, and according to physics, particles that are charges, unlike charges, attract. Yeah. So positive tends towards negative, negative tends towards positive. And now gamma, so that means beta rays go towards the negative, positive. Sorry, while gamma rays go towards negative. Why alpha rays? Sorry, not gamma. While alpha rays are really affected because they do not have um, they do not have what's it called, charge. They do not have a charge on them. Okay, so another thing is alpha rays affect photographic plates and cause fluorescence. So I think that's unique to everybody. They all affect photographic plates and cause fluorescence. So now the next one, produce strong ionization. So as you can see, this one, beta rays produce less ionization than alpha particles, and gamma produces little ionization. So ionization decreases as you tend towards the right. Ionization decreases as it tends towards the right. And the reason why ionization decreases is because alpha particles are positively charged, and positively charged um, in chemistry, positively charged, what's it called, ions have stronger ionization than negatively charged ions. So an ionization is just the ability to give ions. So, and because this gets positively charged, so it has tendency to give ions better than a beta ray. So a beta ray was negatively charged, is not likely to give out its electron. Okay, then because gamma rays are not charged, so they are not really bothered about ionization. They produce little or no ionization. Okay, so alpha rays have least penetrating power that they can be stopped by a sheet of paper. They can be stopped by a sheet of paper. They don't really cause so much damage. You can just stop them by a piece of paper. It shows you how heavy they are. Then but beta particles can penetrate cloth, skin, and paper, but can be stopped by a thin sheet of aluminium. So aluminium stops beta rays. But for gamma rays, you need a lead block, like a lot and lots and lots and lots of what lead block. Shows gamma ray is very, very powerful, and it can travel long distances. Very, very powerful and can travel long distances. Okay, so alpha rays have the biggest mass and charge. Yes, they're very heavy. That's why they don't really travel that far. Beta rays have smaller mass and charge. They have really they have a negligible mass. Really, they have a negligible mass. Their mass isn't really something to something that we can just ignore. But they have a charge. A small charge actually, small compared to the alpha ray. And yes, and then gamma rays have the smallest mass and zero charge actually. They don't even one. Gamma ray is the worst. Negligible mass, negligible charge. Okay, then they can travel, alpha rays can travel 2 to 4 centimeters. Like I said, they can't really travel that far. Beta rays can travel farther than alpha rays, and then gamma rays travel the farthest, travel up to 500 meters. Up to 500 meters. And the last is just their charge, the magnitude of their charge, plus 2 for the alpha, minus 1 for the beta, and 0 for the gamma rays. Okay, so now that we have explained and gone through alpha rays, beta rays, and gamma rays, so the place where question comes out most of the time is from half-life. Half-life. That's where majority of the question comes from. Majority of the question comes from what? Half-life. Majority of the question comes from what? Half-life. So that's just what we'll be jumping into right now. So what is half-life? What is half-life? So the previous slide indicated here that half-life is the time taken by radioactive element or a substance to disintegrate or break up into half of its original or initial mass. Half-life is the time taken by a radioactive element or a substance to disintegrate or break up into half of its original or initial mass. So, for example, if I have 30 grams and then it takes me 6 days to shed half of that, so to reduce to 15 grams, then my half-life is about 6 days. And it is always constant. It's constant. It does not vary. So if it takes me 6 days to get to 15, from 30 grams to 15, and it takes me 6 days to get from 15 grams to 7.5, and so on and so forth. So that's what half-life is. Now, question now is, what is the formula for half-life? What is the formula for half-life? So I'm just going to open my whiteboard here. So sorry, just give me a moment. I'm just going to open my whiteboard. Okay. Sorry, let me just erase this whole thing. Okay, so now the formula for half-life is pretty simple actually. Formula for half-life is pretty simple. So what I have is what? T half is equal to 0.693 over lambda. So T half here is my half-life, and lambda here is a decay constant. So that's just the formula for half-life. That is the formula for half-life. So then another thing you might be asked to do is to calculate the percentage of a nuclei that will remain after a particular set of half-lives. So that formula is just pretty simple. All you just need to do, so your percentage is equal to, the percentage is equal to, let me use a black pen. Percentage is equal to, so again, is 1 over 2 raised to the power n times 1 over 2 raised to the power n times 100. Yeah. Times 100. 1 over 2 raised to the power n times 100. So the same as 100 over 2 raised to the power n. Straightforward. So that's just it. So from there, we're just going to jump into questions from the EdSofta app. Okay, so first question we are going to have. Okay, so let's just start from there are a lot. Okay, so this is a feature on the app called Saved Questions, where you can save some questions that you want to get back to. It's a very good feature on the app, and then it goes further as even show the explanation and everything you need. Okay, so now look at this question. It says the time it will take a certain radioactive material with a half-life of 50 days reduced to 1 over 32 of its original number is. So actually that is pretty easy to figure out, and I'll show you how. So now the thing is, it takes it what? So they told us that the half-life is 50 days, right? So let me just switch back to the board. Okay, so now they're giving us the T half as what? 50 days, right? Give us T half as 50 days, okay? So now, I know that if, let's assume the mass is X, right? So it will take me 50 days to get to 1 over 2 of X. And it take me 100 days to get to, divide this by 2. That's what? 1 over 4 of X. I go on and on and on and on and on. So for me to have 1 over 32 of X, what does that mean? That means I have gone through this thing. This 32, how can I write it in terms of 2? Because as you can see, there's a pattern here. I can write this 1 over 4 here as what? 1 over 2 raised to the power 2x. So now how can I write this 32 in terms of 2? This reminds me of what? 2 raised to the power 5. So that means this, it took us what? We went through this whole thing 5 times. Do you understand? It splits 5 times, splits 5 times. So if it splits 5 times, that means it's going to take it what? 50 times 5, which is what? 250 days to actually get here. 250 days to get there. Very straightforward. Radioactivity, honestly, is not really a very hard question to do in JAMB actually. It's just pretty simple. It's as simple as that. The next one, a piece of radioactive material contains 1020 atoms. If the half-life of the material is 20 seconds, the number of disintegrations in the first second. Okay, so now I did not bring up this formula actually. So, and this formula is just telling us the number of disintegrations actually. That's how we calculate it. Number of disintegration. So what do? Number of disintegration is just simply your decay constant times 10 raised to power your half-life. That's just it. Your decay constant times 10 raised to power your half-life. So what that does is it gives you the number of disintegrations in the first second. Okay, so if you do 0.693, I'm just open up the calculator right now on my end. If you do 0.693, divided by 20, what you get is what? 0.03456, which is what you got here. And then you just multiply by what? By 10 raised by what? 20. So if you want to find the number of disintegrations, always note, find the number of integrations, you find the decay constant, which is what? 0.693 divided by the half-life, because formula for half-life is what? 0.693 divided by the decay constant. So that it just makes sense for the decay constant to now be equal to what? 0.693 of the half-life. Okay, so yeah, so that is that for that, and that's how they got 10 per 20. And then if you put it in standard form, this is what you get. Okay, so okay, no, this is not. So now X-rays can be used in study of crystal structures because they have, see, as you can see, they have what? Extremely short wavelengths. That's why they use X-rays to photograph our bones and stuff like that. They have an extremely short wavelength. So as the wavelength of X-rays is of the same order as of interatomic spacing in crystals, it can be used to provide the imagery of crystal structures. That just goes to explain why X-rays are used instead of gamma rays or alpha rays and stuff like that. Sorry, let me. Okay, so look at this. A reactive substance has a half-life of 20 days, right? So what fraction of the original radioactive nuclei will remain after 80 days? Pretty simple, piece of cake. So what do you do? So the first thing you do is figure out how many times would it have split for it to. So I have my half-life is what? 20, if I'm not mistaken. My half-life is 20 days. So how many times would they have split? Sorry, my half-life is, see, half here is 20 days. Okay. Okay. So now, how much would it? How many times would it have split before we got to for it to have gone towards 80 days? That's just simply 80 divided by 20, and that gives me what? 2 year 1, 2 year 4. We would have split what? 4 times. Now that I know it will have split 4 times, I put it in this formula. Remember, so that means the fraction remaining will have been 2 raised power 4, which is what? 1 over 2 raised power 1 over 16. So the fraction remaining would be what? Fraction remaining would be 1 over 16 of the original 1 over 16 of the original value. Over 16 of the original value. So the answer here would be C. Okay. Then there's a question I've been trying to find. Yes. Okay. Now, in the reaction above, right? Okay. So what we have is we have uranium with mass number 235, atomic number 92. So we have bombarded it with a neutron, okay, which has a mass number of 1 and 0, atomic number of 0 and mass number of 1. And what we get is we get barium, we get krypton, barium, krypton, and something. Okay, so now this thing is just a case of balancing. And what does that mean? That means if you add the mass numbers here and the atomic numbers, it should be the same as the mass numbers on the left hand side and the atomic numbers on the left hand side. So that means the sum of the total here is 236. That means I should have what 236 here. So if I add 144 and 90 together, what do I have? I have 234. I have 234. So that means I'm missing what? 2. And now they've already put 2 in front of here. That means the mass number of this thing has to be what? Has to be what? 1. Okay. So the mass number has to be 1. Okay, then let's move on. So if I add this, I get 92. If I add this also, I get 92. So that means it would not have a mass number, but you have it won't have an atomic number, but will have a mass number of what 1. And the only guy that fits that description is what? Neutron. As you can see, this goes to prove. So neutron, that's the only person that can fit that description. So neutron here is my answer. Let me see if I can find another question like that also. Okay, now look at this also. I have sodium, right? And I bombarded it with something. And what I got was iron. No, sorry, no, this is not iron. This is fluorine because it's 9 and helium. Okay, so now remember the atomic numbers and the mass numbers on the left hand side must be the same as the atomic number and the mass numbers on the right hand side, right? Okay, so now, 9 plus 2 on this left hand side is what? 11. Okay, and then we have 11 here. So that means this guy does not have what? An atomic number. Okay, good. So now 20 plus 4 gives me what? 24, right? But I have what? 23 here. So that means he has a mass number of 1. And who fits that description? The only person that fits that description is neutron. Yeah, it's a neutron. Neutron should be the answer. Neutron should be the answer. The only person that fits that description is a neutron, because 9 plus 2 is 11, it has 0 atomic number, and then 20 plus 4, 24. So that means we're missing a mass number here of what? Of 1. Okay. So, any questions? Any questions? Do you have questions for me? Questions on radioactivity? Is there any question for me on radioactivity? Anybody? Questions on radioactivity? Okay. Sorry, this person wrote, please, sir, Half-Life 2. Have I not spoken on Half-Life already? Do you want me to go over it or something? Does anybody have any questions on radioactivity? Nobody? Questions on radioactivity? Okay, so half-life, I think, or although I think I said something earlier before, but okay, so let me just say it again. So half-life, okay. So definition of half-life. What's the definition of half-life? Half-life definition of half-life is the time it takes for an element, or for an element to reduce in its mass by half. Is the time taken for it to reduce, or to break up, or to disintegrate into half of its original mass. That's half-life. And the formula for half-life is pretty straightforward. Formula for half-life is pretty straightforward. Let me pick up my board. Formula for half-life is pretty straightforward. As I've indicated here, this is the formula for half-life. Okay, 0.693, which is lane 2, 0.693, which is lane 2, over our decay constant. 0.693 over our decay constant. So sometimes they usually give you the decay constant if they need you to solve it like this. So that's just, if they want you to find the half-life, then they give you the decay constant. And I've said so in an example here, in the app where I opened up the EdSofta app. Told us an example. I showed us an example. So this is, let me see what I can find. So there are various, let me find an exact example. Okay, look at this now. A radioisotope has a decay constant of 10 to the power minus 7. The average life of the radioisotope is, average life same as half-life. So what you just simply do is 0.693 all over 10 to the power minus 7. That's just it. 0.693 all over 10 to the power minus 7. And when you do that, you get what? Sorry, 0.693 times 10 to the power minus 7. And then you now have 0.693 times 10 to the power 7. And then you use one of them. So the answer is 6.93 times 10 to the power 6. So this should be the answer without the minus. That's just it. That's just half-life. And then if you want more explanation, you just need to rewatch, because I've done a couple of examples already before. So you just need to rewatch this example, the video, so that you can follow through. Okay, so is there any other question? Is there any other question? Is there any other question? Anybody? Okay. Anybody? So I'm just going to wait an extra minute or so. Does anybody have any question at all? Anybody? Questions? Anybody questions? Okay, no problem. So I think we are done with radioactivity. Okay, thank you very much for your time.